One way to get information about the system's vibration modes is to investigate its impulse response. That is basically by giving the system an impulse like this and investigates its response to this impulse. In that way you will get information about the critical frequencies, the sensitive frequencies, and the characteristic vibration patterns. Another way to get the same information is to investigate the conditions for the existence of large amplitude vibrations even when the excitation is small amplitude. So in this case I excite the system and the vibration response amplitude is not that high, but if I select another frequency I get the high amplitude response. So what are the conditions for getting a high amplitude response even though the excitation amplitude is small? That is what we are going to investigate in this presentation. And we are also going to compare the results obtained from these two methods. Let us begin with a brief recapitulation on how we can use the pole residue analysis to achieve information on the system's modes, vibration modes. So what we basically do in the pole residue analysis is that we start with a transfer function of the system, and then in the end we arrive at the free vibrations of the system, from which we can yield the information about the vibration modes. In more detail, what we do when we start at the transfer function representation is that we make a Laurent series expansion and achieve a pole residue form of the transfer function. Then this is very easily inverse Laplace transformed to obtain the impulse response functions of the system. And from the impulse response functions we can simply use physical knowledge on the behavior of systems in order to achieve the free vibrations of the systems. And from the free vibrations we can make conclusions on the modes, the vibration modes of the system. And as will be shown later on in the course, this kind of route, that is the starting from the transfer function and go via the pole residue expansion, is very, very commonly used when we use measured data to determine the vibration modes of the system. The traditional approach to investigate the modes, the vibration modes of the system, is to use and solve and analyze the eigenvalue problem of the system. So this is an alternative route to find the system poles and mode shapes. So we are about now to see how we can solve the eigenvalue problem for the system. So the idea here is that we actually want to get information about frequencies, excitation frequencies, for which small excitation amplitude will give a large amplitude response. Because these are, the resonance frequencies which are related to the poles of the system. Secondly, we know from experience that the mode shapes, the characteristic vibration patterns, will be dominant at resonant oscillation. So the eigenvalue problem tries to make use of these two ideas. And so we try to solve the eigenvalue problem based on the idea that the eigenvalue problem will give us eigenvalues that are more or less the system poles, and that the eigenvectors is more or less the mode shapes. And if, well, in the best of worlds, these results will be identical to the pole residue approach. So then we have found two different routes to the same results, and that's the optimum situation. So let us now illustrate this with a multiple degree of freedom system. If we write the governing equations in this form, matrix vector form, it's the inertia forces, friction forces, and stiffness forces equals the external exciting forces. On Laplace domain form, we can rewrite it in this way. And the eigenvalue problem, where we require small excitation to give large responses. So small excitation means that the right-hand side, the exciting the force vector, should be small in amplitude, and that the response vector, x here, becomes large, even though the force is small. So in the limit case, we could try to solve this equation for zero excitation. So the right-hand side vector here is zero. Then we obtain an eigenvalue problem. So the eigenvalue problem that we have to solve is like this in the Laplace domain. So this is a homogeneous system of equations. So from linear algebra, we know that we can find non-trivial solutions, that is, solutions that are not identical to zero. Those exist for a homogeneous problem only for values that satisfies the characteristic equation, where the characteristic equation is that the system determinant, in this case this, should be equal to zero. So this is the characteristic equation. And when we have determined the values, the eigenvalues, we can introduce the eigenvalues in the system equations, in this system here, and solve for the eigenvector x. So the eigenvector xn here is actually the solution when you introduce the eigenvalue Sn in the system equations, in the homogeneous system equations. And this solution vector is denoted the eigenvector. So for each pole, there is a specific eigenvector. So, for example, if you consider 2-degree of freedom system like this, we can state the governing equations in the Laplace domain like this. We have the exciting force F1 acting on mass 1, F2 on mass 2, and we have the inertia force, the friction force, and the stiffness force acting on mass 1, and so on. So this is a linear system of equations. And the eigenvalue problem, if we replace then the exciting forces with zeros, that is the limit case then with for the system without external excitation force, then we obtain this eigenvalue problem. So the characteristic equation where the system determinant is equal to zero is is like this. In principle, the system determinant for a 2x2 matrix is, the diagonal terms, the product of these, minus the product of the off-diagonal terms, like this. And that is what is given here. And if you remember now the transfer function denominator, that is actually identical. The polynomial in the denominator of the transfer functions is identical to the left-hand side in the characteristic equation. So when we look for the system poles from the transfer function, we set the denominator equal to 0. So this is actually identical to the characteristic equation. So we can conclude then that the eigenvalues are identical to the system poles. That's good so far then. So what about the eigenvectors then? Does the eigenvectors, are they equal to the mode shapes that we obtain from the residues in the pole residue representation? From linear algebra, we know that the eigenvalues give linearly dependent equations. So if we insert one of the eigenvalues, Sn, in the system equations, then we will have a linearly dependent system equation. In our case, it means that both two equations yield the same information about the system. So we can it's enough to use only one of the equations. And in our case, the first equation is the simplest one. So we use this one. This is the first equation in our system. So if we insert the eigenvalues, well, one at a time, so let's insert the eigenvalue Sn, and then we let x2, for instance, be equal to some constant, let's call it phi, and then we solve for x1, and we obtain this. So x1 with x2 equal to phi must satisfy this. And S here, of course, is the pole. So if we put this on vector form, we have the eigenvector xn equal to this factor phi and times a vector with the first component equal to x1 and the second component equal to 1 or phi. So here we have the pole, and this phi here is arbitrarily chosen scale factor. So we have a shape vector here, an eigenvector or shape vector that sort of gives the relative size of the components in the vector. So the factor in front of is a scaling factor that can be chosen in any way you wish. So let's now study a numerical example. Let's say that the masses m1 and m2 are 1 respective 2 kilograms, and that the stiffnesses are 2 kilonewtons and 1 kilonewtons. And let's start with the simplest case where the damping is 0. So d1 and d2 is 0. So we have a lossless system. So the roots of the denominator, the pole pairs, are in this case real. They are purely imaginary, and as you can see, they are complex conjugates. The corresponding eigenvectors looks like this. We have the eigenvector corresponding to the pole S1 is equal to this, and to pole V2 is like this. And we get the same results for both these sign alternatives. So both the positive and negative signs gives the same eigenvector. Okay, so if we go via the pole residue, the transfer function approach, then we find that the residue pairs for pole 1, that is S1, looks like this. So this is the residue obtained if you study the transfer function between the force on mass 1 and the response on mass 1. Then you will get this pole pair. And if you study the transfer function between force on mass 1 and the response x2 on mass 2, then you get this pole pair. Residue pair. So for pole 1, you find this residue pair. And from this you can construct the mode shape matrix. And from pole 2, you find a second mode shape matrix from a combination of this second pair here. So we find this residue pair. These mode shape vectors from the residue pairs. So this and this is actually corresponding to this and this. The only difference is that it's multiplied with a factor of 100. And this is from the second pair. This and this. So, if you now rescale the first vector here, so that the second component becomes 1 in both cases here, then you will find that the mode shape vectors will look like this. So one with both positive and one with negative and positive. And you will be able to see that this is in fact identical to the eigenvectors obtained from the eigenvalue problem. So that's good. Now we know that for an undamped system we get exactly the same eigenvectors as the mode shape vectors. So what about proportional damping then? That is when the damping matrix is a factor times the multiplied with either the stiffness matrix or the mass matrix. So let's check now what happens if we introduce a damping D1, which is for instance 20 newtons per meter per second, and a damping D2, which is 10 newtons per meter per second. So as you can see now, the damping matrix is directly proportional to the stiffness matrix. It's a factor of 1000 that differs between these. The roots of the denominator, that is the characteristic equation, gives us these pole pairs, and as you can see, they are complex conjugates. But the difference from the undamped system is that now we also have a real part here, and that is of course due to the damping, to the losses of the system. So this part, this real part, will, as we have discussed earlier, give us the decaying behavior of the impulse response. The eigenvectors will be like this, and as you can see, these are identical to the eigenvectors of the undamped system. And that is characteristic for the proportional damped systems, that the eigenvectors are the same as for the undamped system. So what if we use the residue pole approach, the transfer function approach? Well, we obtain following pairs of residues, and in the same way as we did before, we can construct our mode shape vectors from this and rescale, and we will find then after the rescaling that once again the mode shape vectors are actually identical to the eigenvectors. So far so good. So next step then is to check what happens if we have non-proportional damping. This is actually the most general case then. So let's now try this data, that we have D1 equal to 10 newtons per meter per second and D2 equal to 20 newtons per meter per second. Now this damping matrix is not proportional to the stiffness nor to the mass matrix. The roots of the denominator now, or the pole pairs, is like this, looks like this. And once again you can see that we have a real part, since we have damping in the system, and that the pole pairs are complex conjugates. And like we have said before, the imaginary part now will give us information about the resonance frequency of the system. If we now calculate the eigenvectors, we will find now that, well, if we consider only the real parts, actually the eigenvectors will be approximately equal to the undamped systems. But the main difference is now that we have an imaginary part of the eigenvectors. So the eigenvectors in this case for the non-proportional damped system is not equal to the undamped systems. We have a difference. And if we interpret this in a physical manner, then we will find that this imaginary part here will introduce, well, corresponds to a time lag between the motion of the two masses. So that means that they will not reach maximum or minimum at the same time. There will be a phase lag between the signs that describes the motion of the mass 1 and mass 2. If we go for the residue approach, we find the following poles following pole pairs. For pole 1, we find 2 residues for the 2 different transfer functions, and as you can see, they are complex conjugates, as it should be. And for pole 2, we find this. So from the residues now, we can form 2 eigenvectors like this, corresponding to pole 1. This is the mode-shaped vector, and for pole 2, this is the mode-shaped vector we obtain. So if we rescale, like we used to do, to make the second component equal to 1, we find this mode-shaped vectors. And they are, as we have hoped for, identical to the eigenvectors. To the eigenvectors we obtained from solving the eigenvalue problem. So that's very good. So we can conclude now that the poles are actually equivalent to the eigenvalues, and the residue vectors are identical to the eigenvectors. So the results we obtain from the transfer function approach are actually identical to the results we obtain from the eigenvalue problem approach. Very good. So that's all for now.